get rid of this. Okay.
Okay, thank you everyone for coming to the workshop today, and thanks again for Mondi to give such a fantastic talk to start the very exciting symposium today. And we have seen quite interesting topics on the large language modeling and also the diffusion model with guidance in the generative AI. And then in the next talk, we'll have like Professor Qing Cui from the University of Michigan to talk further along this line and also some theoretical study very interesting about the generative AI. So just to give a quick and brief introduction for our next speaker. So Professor Qing Cui is an assistant professor in the X department at the University of Michigan, Ann Arbor. And prior to that, he was the data science fellow in the New York universities and also got his PhD from the Columbia universities in the electrical engineering in 2018. He also received a bachelor degree from the Tsinghua University in the 2011 and master degree from the GHU in the 2012. And his current research mostly focused on the deep representation learning and also the diffusion models. And he also has got a very long list of the awards showing here. So let's welcome Professor Qing Cui for the next talk on the emergence of the generalizability and the semantic low-dimensional subspace in the diffusion models.
Okay. Yes. Thanks, Li Yue, for the great introduction. So in this talk, I want to talk about this topic, continue Mondi's discussion on diffusion models. And some of the work is inspired by Mondi. So I think starting from this Google's imaging like DALI models, right? We witnessed the revolution by diffusion models for image and video generation. And I think one of the nice things with diffusion models is that we can control the generation in different ways, right? For example, for OpenAI study model, we can use text to guide the generation of images, and we can use gradient guidance to solve inverse problems. And recently, the ICC best paper shows that we can control using some sketch to guide diffusion models to generate images. And later on, early this year, we saw the Sora model from OpenAI, right? We can use diffusion models to generate videos. So there's a lot of excitement in diffusion models, but what does it really works? I think Mengdi has already briefly talked about this. So the basic idea of diffusion models involves two processes. So one process is relatively simple, is that to generate image, so first, starting from image, we'll gradually adding noise to destroy the structures until it become a total pure noise. And afterwards, but the important part is the backward process. So the backward process is starting from some Gaussian noise. We want to reverse the process of through denoising, right? Gradually remove the noise to generate image. And this forward and backward process can be described using stochastic differential equations. If you taking the t, the discretized version into continuous by considering t to be very small, the forward process can be described by this stochastic differential equation, right? And dw is a Brownian motion that you gradually adding noise to the image until it reaches a pure noise. But later on, some statisticians and recent work by Song Yang's group, they show that this forward process of adding noise can be reversed. So the reversal is really depending on the score function or the gradient, the staying the staying function where the gradient with respect to x for every t, right? So if you know the score function, the gradient of the log likelihood of every t, then you can reverse the process starting from the noise to generate an image. So this is nice, but the question is, how can we know the score function, right? So here, the image distribution is not known ahead of time. And here you are asking that we want to know the distribution across every time of t, right? That's a very challenging problem. And the idea of solving this reverse process from a noise to image is that we know that the neural network is a universal approximator, right? So why not we use a neural network to approximate the score function for every t, every time step, where t is denoting the noise level, right? And so the idea is simple, is that we just use a highly overparameterized neural network to approximate the score function across every time step t. And initially, if you look at Stable Diffusion version 1 and 2, a typical choice of the neural network to approximate score function is a UNet-based architecture. And more recently, if you look at Sora and Stable Diffusion version 3, people are starting to adapting to transformer-based models. And I think the reason people is shifting from UNet to transformer is because transformer satisfies the scaling law, right? We can scale it up. And also transformer is a better model to unify text and image and different modalities. So this is nice, right? The idea is to use a neural network to approximate the score function. But the question is, how do we train such a neural network, right? And in terms of training, so basically the idea is just we minimize the distance between the score function for every time step t versus the neural network parameterized by theta. However, this is still intractable, right? Because we don't know the score function for every time step t, right? We don't know this underlying oracle score function. If we know that, the reverse process is already solved. And we can deal with this through Tweedy's formula, is that the noise we are adding every time is Gaussian. And you can show that by Tweedy's formula. So the original loss function in terms of expectation can be reduced into a predicting noise using our neural network. So here epsilon is just a pure Gaussian noise. And you can show that actually these two loss functions, they are equivalent. And essentially, this is a more tractable loss function for approximating the score function using a neural network. And to optimize the loss function is relatively simple, right? You just draw some samples and take stochastic gradient descent, sorry, not descent, stochastic gradient to minimize or train the neural network. However, there's so many questions lingering for diffusion models, right? So neural network is a black box model. So firstly, we want to know there are many questions that has not been answered in training and sampling from diffusion models. So first of all, is a question about generalizability. Is typically we train our diffusion models on the finite samples of training data points, right? And we cannot expect, we can expect that diffusion models can reproduce the points from the training data. But why diffusion models nowadays can generate samples that are very different from the training data set? Right, this is something like it's puzzle and unclear why diffusion models can generate new samples from when we train a finite number of training points. And this really cares about the generalizability of diffusion models. Secondly, so although there's many ways of controlling diffusion model generation, but so those generation control is either ad hoc or it's a very coarse control, right? If you're given a text input, right? In many cases, if you try the DALI model, right, it doesn't generate the things that you desired, right? So how can we precisely control and manipulate the generation of diffusion models is something very challenging. And in this talk, we are trying to answer, trying to probe into those questions about generalizability and controllability of diffusion models. And our viewpoint of those questions is through the low-dimensional structures in the model and the data. And specifically, this kind of union of mixture of low-rank Gaussian models that we are starting through such a model to provide insights into how can we enable generalization and how can we control diffusion models. But first, I want to start with an intriguing phenomenon that we find, which is called the reproducibility phenomenon in diffusion models. So first, I want to start with this paper. So this is a paper that we get accepted at SML this year, and we get the Best Paper Award in Diffusion Model Workshop last year. So I want to start with a question. So suppose you're starting from a noise. You're starting from the same noise for two different diffusion models. And those two different diffusion models, one can be a U-net, another can be a transformer, and they are trained on the same training data set. And during the sampling process, you are starting from the same noise, through the same ODE sampler, and you generate two images, which is image one and image two. So my question is that, how does these two images relate to each other? Any guess? Yeah, so
The same structure or no?
yes, that's exactly right. So actually, you will show that if you're starting from the same noise, actually they will generate very similar images. So this is why we call it reproducibility in diffusion models. And we show this actually is quite prevalent phenomenon in diffusion models, is that if you look at UNet, vision transformer-based models, different training losses, and if you compare the generated images from different noises, right? So if you compare, this is the same index here is corresponding to the same image, you will see that the generated content actually is very similar to each other. But this is only like a visual illustration, right? So how can we quantitatively showing there's a strong reproducibility there? So the idea here is relatively simple, is that, so say you have two different diffusion models, and you generate two images, you want to measure the similarity. What you do is that you get rid of the scaling and all kinds of invariance in your generation through a neural network, right? You use a self copy detection neural network to map into the latent space, and then you measure the cosine similarity in the latent space of a neural network to measure, to count for the similarity between two images generated from two different diffusion models. And based on this, if we want to evaluate the reproducibility like robustly, right? So here, this similarity is only measure the similarity for one image, right? But here we want to measure the reproducibility between two models. How to measure this is that we generate many images and we take an average, right, to measure the similarity. So here in practice, what we do, and we define a reproducibility score, is that we're using this cosine similarity or this MSCD metric to measure the similarity between x1 and x2. So if the similarity is larger than certain threshold, we say that there's a high reproducibility, right? And in practice, we empirically evaluate this probability, right, to count for the reproducibility between two models. And what you'll find is that actually this reproducibility is pretty prevalent. We studied the reproducibility between different architectures, different training losses, sampling procedures, and perturbation kernels. You will see that there's a very strong reproducibility between all different type of diffusion models, right? And the slowest point is 0.7. You remember the RP score is a probability measure. It's between 0 and 1, right? And we did an even more comprehensive study of this, right? You can see there's a very strong reproducibility even you train on different, all kinds of type of diffusion models. However, I want to emphasize is that this reproducibility actually is pretty rare in generative models. If you consider GAN type of models or variational autoencoders, and you measure different reproducibility between different GAN models and different like VE models, actually there's a zero, almost zero reproducibility, right? But if you look at diffusion models, so this is reproducibility actually is very strong. And actually there's a concurrent work from Stephen Malad and Errol Simoselli, where their work wins a clear outstanding paper this year, where they showed a very similar, complementary results to ours, that they trained the same diffusion model from non-overlapping subset of the same like training data, where S1 and S2 are drawn from the same training data set, but they are the subset of those data set with non-overlapping training points. And when the number of samples is small, you see minimum reproducibility between the images. But when you're increasing the number of samples, right, and when you're starting from the same noise, you generate samples, you will see that actually the images generated actually are very similar. They look very similar. Even they are trained on the same training data set, a non-overlapping data set. But unfortunately, our paper also submitted to ICLR and get rejected. So here, in comparison to their work, actually we take a further step to look at how the model capacity affects the reproducibility, right? So here, what we did is that actually we find the reproducibility is strongly depending on the size of your training data set. So here we did an experiment. So the x-axis is a number of training data points. And the y-axis is the reproducibility score. And what you can see here is that we are comparing the reproducibility between different type of diffusion models. And you can see that the reproducibility at the beginning, when the training data set is small, is very large. And then when you're increasing the training data set, it diminishes. And when you further increase the training data set, it re-emerges again. So you will see that actually this reproducibility emerges in two different stages or phases. And this reproducibility actually co-emerges with the generalization of diffusion models. So here, this is another figure that we ran in the same setting. So here we are trying to measure when the diffusion model generates new samples or when diffusion model generalizes. And so y-axis is again the training, x-axis is the training data set. So here the difference is that we are trying to measure the generalization of diffusion models. So how do we measure the generalization? So here we introduce a very simple definition. So we define generalization as, so say we have a diffusion model generate a new sample X. we are trying to measure how the generated sample X different from the training data set. So if X is very different from the training data set, then we say that this is a generalization. Or if it's very close to one of the training points, we say this is a memorization. And our GL score basically measures how X is different from all the training data points. If X is very different from all the training data points, then GL score will be equal to 1. If X is very close to either one of the training points, then we see this is a memorization. And the GL score will be equal to 0. So if you look at this figure, right, in the first phase, we have a memorization, right? The GL score is 0. But actually, I think this definition is not very precise. So per René's suggestion, so I think this should be a memorization score. So I will just list here. So if you put these two figures together, you will see there are some patterns, interest patterns occurs, right? So when the training data set is small, we have memorization, right? And we have a strong reproducibility. And when you're increasing the training data set, you can see that the emergence of generalizability corresponding to the re-emergence of reproducibility, right? So there are some very intriguing, interesting phenomenons is that this reproducibility phenomenon actually emerges in two distinct regimes. One is, and it strongly correlates with the generalizability. So this is induce a question is that why we have generalization when we have a reproducibility, or how can we lead based on this reproducibility to understand why diffusion models generalize or generate new samples. So this, you need to look back into the ODE sampler, like how do we sample from a diffusion model, right? So if you look at the sampler, right, basically we are using the neural network to approximate score function. And so the reproducibility basically means that all diffusion models are learning the same score function, and that's why they generate the same sample, right? But this is only answer the first question. So the second question is that if you want diffusion model to generate new sample, right? So it's corresponding to what kind of distribution you are learning such a score function. So whether the distribution is an empirical distribution or the distribution is underlying data distribution, right? This matters for generalization, so generate new samples. So in the memorization regime, right, if you look back this reproducibility in the memorization regime, so is a very intuitive is that the diffusion model is learning the empirical distribution. Or in other words, the diffusion model is learning the multi-delta distribution of your training data set, right? We can quantify the multi-delta distribution of your training data set by something like this, right? So here it is, each yi is one sample in your training data set. And the empirical distribution of your training data set can be written as a multi-delta distribution of your data points, right? And it will be something looking like this. And you can imagine that if diffusion model is only memorizing or reproducing training data points, basically diffusion model is learning this empirical distribution of your data. And you can think that the diffusion model from memorization to generalization could be that you're increasing the number of data points. When the number of data points is large enough, then you reach generalization because the empirical distribution will approximate the true data distribution. And then we will generalize, right? We will generate new samples. And this could be an explanation of generalization in diffusion models. But is this true? Well, I think if you are going this route, it's a little bit pessimistic because usually our images is very high dimensional, right? The D of our images, so we're using D to denote the dimension of our data. So usually this D is very large, and if you want empirical distribution to approximate a true distribution, So you will see that actually the number of training samples you need for the empirical distribution to approximate the true distribution to an epsilon closeness will growing exponentially with respect to the dimension, right? So it doesn't seem to be possible that this underlying distribution, empirical distribution, can approximate with finite number of samples when the dimension is very large. But however, if you look at this generalization score, you will see something quite surprising is that when the diffusion model from memorization to enter generalization, the number of sample you need actually is not that large. It's only around 10,000, right? It's much smaller actually than the worst case that you require to enter generalization, right? So why does this happen? So why we only need finite samples to generate new samples when training diffusion models? I think this question can be answered through the intrinsic low dimensionality in your data and model. But let's first look at the model. Actually, you will see that actually this model has intrinsic low dimensionalities. So here, let's consider the rank ratio of the Jacobian. So here, x theta is a mapping from xt. It's a denoising autoencoder mapping from xt to the clean image. So x theta is the mapping from xt to clean image. And here we are considering a different variant of this score-based diffusion models is that we are considering training x theta, which is a mapping directly from xt to the clean image, because we want to understand the intrinsic dimensionality. That's why we consider the mapping from xt to x0. And so the x theta actually is strongly correlated with the score function through this Tweedy's formula, right? So here you can see that x theta is correlated with the score function through the Tweedy's formula. But let's go back and look at this Jacobian of this mapping from a noise to an image, and you consider the rank of this Jacobian. And here, what I'm plotting is the rank ratio between the ratio between the numerical rank of the Jacobian versus the ambient dimension. And the y-axis is plotted in the log scale. And you can see that starting from, and this SNR is image to noise ratio. And you can see that starting from the noise, then the rank is decreasing dramatically to 10 to the minus 2, 0.1. So which means that the Jacobian is a very low rank in the middle of the noise step. And then we are getting back to image, it's becoming a more and more like an identity mapping, then it's getting high rank. But if you look at something in the middle, right, the Jacobian is very low rank. So actually this is a corresponding to the intrinsic dimension of your data set. So indeed, as Mengdi mentioned, right, so the low dimensionality or the low rankness of Jacobian reflects that intrinsic dimension of our data actually is very low. And there's a work by Tom Goldstein group that they're trying to measure the intrinsic dimension of different kinds of image data set. They will show that actually the different data sets actually, even on ImageNet, the intrinsic dimension is very low. And if you look at all the CFAR and MS COCO, actually they are around 10 to 12 to 20 to 30. So, so go back to our original question, right? Why diffusion model can generate new samples with just a finite number of training samples? This strongly embedded in the intrinsic low dimensionality of our data set, right? So the number of sample you need to enable generalization is scaling not scaling with your ambient dimension, but is scaling with the intrinsic dimension of your data. So to study the scaling laws or the scaling of samples of generalization in diffusion models, we started with some simple model, which is called this mixture of low rank models. And you can consider this model as a special case of what Mengdi just mentioned, his SML work. And the reason we started such a mixed low-rank Gaussian model is because the mixed low-rank Gaussian captures intrinsic dimension. On the other hand, this is a model that is simple enough. We can derive the closed form and analytical solutions of the score functions, right? If you study the original image distribution, the image distribution is too complicated. It's very hard to say anything. But here, if you want to quantitatively study it, we need to start from simple and analytical distributions. And that's why we assume our data is following this mixture of low-rank Gaussian, where each Gaussian is rank, the covariance matrix is rank deficient. And this UI, you can think of as a basis of the subspaces of our data. And for this mixture low-rank Gaussian, because it's simple enough, actually you can calculate the expectation of xt to x0, or this prediction of our original image, and you can show that this expectation actually have a closed form, something look like this. And you can also equivalent derive the score functions for this mixture low-rank Gaussian data points. And on this mixture Gaussian distribution, right, you can train the unit model, and you can, again, plot the generalization score. You can see that actually this generalization is the number of samples you need actually depends on the intrinsic dimensionality, right? So here this dk is denoting the intrinsic dimension of the Gaussian. And when the intrinsic dimension increases, right, the number of samples is increasing. So there's a phase transition from memorization to generalization also on this simple model. So why not let's just focus on this simple model to study the generalizability of diffusion models. So here we derive some results to give you enough intuition why diffusion model generalize. So let's consider where we only have one low-rank Gaussian. So let's just consider where k is equal to 1 and see what happens. When k equal to 1 case, and if we look at the optimal this expectation of the image predictor, you can see that this is something look like this, right? So the idea to study this is why not we parameterize our denoising autoencoder in a form that's very close to the original, the optimal score function. But here, this U and the U transpose are not known ahead. And we want to train the U to predict the image. And interesting thing is that if you take the expectation of our training loss for the denoising autoencoder, and you can show that actually the training loss is equivalent to a principal PCA problem, right? You will show that the training problem actually is equivalent to PCA, right? And we know that the PCA, there's a transition from not learning the basis to learning the basis, right? If you have enough number of training samples, where the number of samples is larger than the intrinsic dimension of our data, of the subspace, then we will learn the basis of the subspace. If you don't have enough data, then you will not learn subspaces, right? There's a clear phase transition that in PCA problem. And because of equivalence between PCA and training diffusion models, so that explains to some extent why there's a transition from memorization to generalization. And this intuition actually can be generalized to multiple subspaces, right? So if we know that if k equal to 1 is a PCA problem, then if you generalize this to multiple subspace where k larger than 1, then you can show that we can parameterize our neural network in a way similar to approximate optimal PMP, and you can show that the training problem for diffusion models is equivalent to subspace clustering, right? And then you can show the phase transition, right? When we're solving the PCA problem, right, and this is a phase transition from not learning the basis to learning the basis, And you can, based on the similar parameterization, and you can show that actually when you're training the diffusion models, there's a phase transition of not learning the basis to learning the basis. And similar to multiple subspaces, right? For subspace clustering, there's a phase transition. And we can show a similar phase transition in diffusion models as well. And more interestingly is that those bases, so if you look at those bases, right, so this U1 to UK, or in the PCA problem, the U here, actually those U's, it has semantic meanings. So here is a visualization, is that we manipulate our image along the basis directions. And you can see that those bases actually has semantic meanings corresponding to gender, head, figure, color, or etc. If you are not, you are choosing an arbitrary direction to manipulate your image, actually it doesn't change anything. So if you have this understanding of generalization, actually they will enable you to control your diffusion models in a more precise way. So next, I want to conclude my talk by using this like insights from generalization to show you how can we control the manipulate the image generation in diffusion models by manipulating the basis in terms of this denoising autoencoder. So I think don't have much time. So here I want to show you some results that what we can achieve, right? So if you understand the generalization and you know the subspace has semantic meanings, you can achieve precise and localized image manipulation. So here we derived a method called low rank controllable image generation, and in short, we call this a local edit. And we can show that our methods can achieve all kinds of precise and localized manipulation of our images. For example, you can manipulate the mouth shape, the hair curve, hair amount, and eye shape, etc. And the editing direction you find actually is very homogeneous and transferable. For example, if you find the semantic direction in one image, right? For example, you can change the eye shape, open, close eyes, and then you just take that direction, and you can use the same direction to manipulate other images of similar, like human faces. And also, our method is very simple. It's just a one-step editing. You just edit your image in one noise level. And say if you find a direction in the noise level t equal to 0.5, you can transfer that direction to t equal to a higher noise level, like t equal to 0.8, right? And you can still enable this kind of manipulation of your images. And more interestingly, because the bases are orthogonal, right? Actually, you can do disentangled and compose the editing directions to manipulate your image, right? If you look at this figure, right? So we can use one direction to manipulate the eye size, and you can add another disentangled direction to our image to manipulate your smile. And this is another illustration that you can add smile and decrease the higher color, for example. And another property of this editing direction is that they are highly linear, right? If you increase the strength of editing or decrease the strength of editing, actually there are resulting linear changes in your images. So in this example, you can open the mouse or close the mouse by editing, changing linearly through the editing directions that you obtained. And this can be extended to text to image diffusion models, right? For example, in stable diffusion and other type of text to image diffusion models, right? So you can use this editing direction to also edit this kind of undirected text to image directions. And you can also enable text supervised direction where you can give a prompt and then you can edit locally, for example, adding glasses, removing glasses, and adding hairs, etc. So I think I don't have enough time, but I just want to give you some intuition how this method works. So this strongly embedded in the understanding of this denoising autoencoder in the generalization part of my talk. So the basic idea is that you want to look into the posterior mean predictor, which is the mapping from the noise xt to the clean image x0, where if you look at this mapping from xt to x0, um, and you do a first order Taylor expansion of this PMP, and this first order approximation expanded at xt is written like this, right? So this is our anchor point of f theta t at xt plus Jacobian of this mapping multiply the direction you are moving, the delta x. And what we'll see is that there is a posterior mean predictor of this PMP that I already showed in the previous section, has very nice properties. So there's two properties you will see in this PMP through this figure. So the first figure we already showed in the generalization part, right? So this PMP is low rank, right? The rank is changing, where from the noise level, high noise level, where is high rank, but in the intermediate step, it's very low rank, right? Another thing, nice thing about this PMP is that it's locally linear, right? If you measure the difference between L theta, where L theta is the first order Taylor expansion between this PMP, you will see that actually is a very highly, it's a linear, almost a linear function, right? You can see this lambda is changing the strength of the moving directions, and you can see that the correlation between the norm ratio and the cosine similarity between f theta and L theta actually is almost around 1. So we can utilize these two properties to enable image editing. And so the basic idea is that if you're moving, say, moving your data x, delta x, where delta x is the direction you want to edit, you're moving along one of the basis directions of the Jacobian. So if vi is a basis direction of our Jacobian, if you are moving along such a direction and you approximate your PMP with a linear, the Taylor expansion, right? And this vi is your editing direction, and you plug the Jacobian of the singular value form, and you will see because of orthogonality of Vg and Vi, where I and G are not equal to each other, you will see that actually this reduces to something like this. So basically moving along the Vi direction will resulting in editing your image along the UI direction, right? UI is also the left singular basis of your Jacobian, right? And we know that UI has semantic meanings. That's why if you're moving along VI direction, you will be editing your images correspondingly. And because these VIs, UIs are all orthogonal to each other, right? That's why you can enable disentangled orthogonalized editing of your images. And another nice thing of the low rankness of Jacobian is that if the Jacobian is low rank, we can do compact SVD, right? We can do generalized power methods to compute the low rank subspace much more efficiently. And that enables efficiency of our method. So this is the overall view of our method. It's much more complicated, but basically we enabled localized editing by adding a mask of our image to mask out the regions that we don't want to edit, and then we only focus on the regions we want to edit through some orthogonal complement projection. And finally, this is a visualization of the editing directions when you're using our method, right? You can see that its editing directions has semantic meanings. It's only editing a small portion of our images. And we compared our methods to all this kind of diffusion-based editing method. And you can see that actually our editing, and this is adding a red lipstick to the human face. And you can see that actually previous methods, the will have some global change of your image, or the resulting something like very artificial, right? But if you look at our image, the editing, right, is more natural. It only changes a very small portion of your image you want to edit. So to conclude my talk, so in this talk, we show that there's a many intriguing phenomena in diffusion models, the reproducibility, and this results in the generalizability, leads to the general understanding of generalizability and leads to a controllability of our diffusion models. And the core of the idea is that the data set we are learning is low dimensional, right? It has semantic it lives approximately in a union of low-dimensional subspaces. And you can, through this viewpoint, right, you can enable controllability of your model. And finally, this is the major references of our work. The first one is published in Clear this year, SML this year. And the rest is we just archived yesterday of our work. And um, and I want to thank all my wonderful students and the collaborators for enabling this line of work. Thank you very much.
Thank you, Qing, for the very fantastic talk. Any question from the audience? Okay, I will go with a quick one, and people can take some time to think about and digest the contents here. So I think it's very interesting to see the no-dimensional structure for the diffusion, and also very cool to see like how this can be used for the image editing. And do you think how this kind of the characteristics or the property of the low-dimensional data structure can be useful for improve like the efficiency of the training or the sampling for the diffusion model?
Yeah, I definitely think so. If you look back to the denoising autoencoder, the rank, right? And actually, this is the initial phase actually is pretty high rank, and then the middle point is very low rank. I think you can parameterize your neural network differently across different time steps. And also, what we find is that when your neural network is pretty close to noise, actually don't need to train your neural network very well. Even you use a Gaussian denoiser, as Xiang showed previously, that actually you use like a coarse Gaussian denoiser is sufficient. But the important part of this denoising process is more closer to the image. We are closer to image, we want to use like a more parameterized neural network. And I think changing the parameterization across time steps can definitely improve the efficiency of your sampling process.
Yeah.
And also training. Yeah.
Yeah, cool. Yeah, looks like auto follow-up work can be done. Yeah, any other questions from people here? Yeah, please.
I wanted to better understand the connection between diffusion models and Gaussians, just the simplest case, or even just the PCA model.
Right.
And what I want to understand is in particular that I expected that connection probably to be known. The reason is if you take the probabilistic PCA model, you turn it into a variational autoencoder. So maximum likelihood for the variational autoencoder will correspond to probabilistic PCA. And so now, if I understood correctly, the diffusion model is a VAE with a structured latent space. But if you choose the network to be exactly with the encoder that comes from PCA, then it has to be the same as
Right. Yeah, this quickly depends on the parameterization. So we simplify the model a lot.
Yes.
Yeah.
So is that the only difference that precisely what I don't understand is that what would have been known would have been just like a one-step diffusion model. And so you seem to have been able to do it for multiple steps, and that's the part that I don't understand. What is the difference?
I think here, actually, our model is indeed simplified. There's some gap between theory and practice. So here, our claim is that if you parameterize this way, you can understand generalization, right? You can see that, I mean, not distribution learning, you can understand that why you learned the mixed or low-rank Gaussian model distribution. But the thing is that in the underparameterized, or so you don't have enough samples. In that case, you cannot understand memorization, right? So this parameterized model cannot lead to memorizing of your training data set. So there's some gap. And also, if you look at this denoising autoencoder, if you look at this curve, so when you're using the parameterized model, you will see that actually this low rankness is pretty flat across all different time steps. But the practical UNet parameterized model, actually the rank is changing. Is either closer to image or closer to noise is high rank. But in our case, if you parameterize the network in the way that we did, the rank actually is flat across all different time steps. So I think that indeed there's some gap. But here, I think this is a first step towards and building some intuition to understand what's going on in diffusion model. But definitely there's a lot of a gap there. Yeah.
Yeah, another question. Yeah.
Yeah, so just adding to the first question, you can show that if you don't have the bottleneck layer, the diffusion model is precisely the same as a variational autoencoder with an infinite number of hierarchical primes. So you can show that again. Because his first point was connection between model and the aids.
Right, right.
So there is a one-to-one correspondence if you don't have the bottleneck layer.
Yes, yes. Yeah. Yeah, thanks.
Just a comment.
Yeah, thank you, Kathy.
Cool. Let's thank Qing again and for the great talk. And to the chance, and we will not ask like more time for the question now because we have the break before the next talk. So feel free to come to the speakers if you